Okay. Now it's being recorded. Let me just share then. Screen share. Okay. So you can see the screen shared. Where did the chat box go? Okay, good. So yeah, so now I'll close down the chat box and I'll turn off the video and we'll start the lecture. And so if you put something in chat box, I won't be able to see. So if I ask for feedback, one of you just unmute and say something. So sometimes, and I'll ask for feedback in the middle because sometimes it may get disconnected and I may not know that we are connected or not. Yeah. Okay. So yeah, so yeah, so this course, as you know, is about rings and modules. And so I'm sure you must have seen the definition of rings, but you may not have studied them much. So probably in linear algebra, you know, in linear algebra, you must have seen what a ring is, or at least what a field is. So a field is a special kind of ring. So let us start with recalling the definition of a ring. So a ring is a triple, R plus dot, where R is a set, and plus dot are binary operators on R, which means they are function from R cross R to R. Yeah, so it's like a group, but there is more structure. Yeah, so in group we have only one binary operator, let's say plus, which satisfies some axioms. Here we have two binary operators on this set, plus and dot. Okay, and they should satisfy the following axioms. So one of the first axiom is this: R plus should be a commutative group, and the identity of R plus we denote it by 0R. The additive identity is also called the zero of the ring. Yeah, so maybe I'll here. Also called zero of the ring. Yeah, so of course this axiom you can expand it. You can throw in all the group axioms together with the axioms about this being a commutative operation plus being a commutative binary operator. So for instance, you have to say plus is this plus operator is associative, and additive inverses exist. So if A is there, then there exists an element minus A in R, such that if you add them, and then you get 0. And the identity element has to be there. So all those axioms you have to throw in. And then for dot, the axioms are less restrictive. So A dot B, it should be associative, and then it should be distributive with respect to. So there should be a relation between plus and dot, these two binary operator, and that relation is that it should be distributive. Yeah, so A dot B plus C should be same as A dot B plus A dot C for all A, B, C in R. Yeah, and similarly on the other side. Okay, so that's what the definition of ring is, and most of the rings we'll study will also have element called the multiplicative identity or unity, ring with So sometime multiplicative is dropped. Identity usually means multiplicative. And for 0, we have, for the additive identity, we just call the 0 of the ring. So what is this? What is the property of multiplicative identity or unity? Is that if you multiply it to any number, you get that number itself. Yeah, for all elements of this ring R. And then, so most rings we'll consider will have this and this multiplicative identity, or will have unity. And when people study more abstract ring theory, then they also assume that the ring may not have multiplicative identity, may not have unity, and but most of the useful rings, useful meaning rings which are, so all these definition came from other areas. So algebra was developed to solve problems in areas like number theory and algebraic geometry and so on. So though the notions are taught to you before algebraic geometry or number theory because they are elementary, but they came after people needed it to make their study of algebraic geometry and number theory more rigorous. Yeah. So the definitions came up a little later, the abstract definition. So R is said to be commutative if for all AB in R, A dot B is same as B dot A. So if when this dot is also commutative, we say it's a commutative ring. So in fact, in this course, mostly we'll study about commutative ring. Not much about non-commutative ring. We'll see 1 or 2 examples here and there, but we'll study mostly about commutative rings. Yeah. So of course, the examples are this Z. So I mean, of course, people studied these objects, integers and rationals and reals and complex numbers, though they didn't call it a ring or a field and so on. So these 3 are fields and Z is a ring. So this, you know.
Sir?
But basically, I mean, everyone knew that what structure they have. They have this addition and multiplication, and they satisfy all these axioms. So all these four are commutative rings with identity, with unity. And this guy is the set of matrices. And we know that this is not commutative. Not commutative. Set of matrices with entries in the real numbers. Yeah. So everyone with me so far? Can someone say a word or something?
Yes, sir.
Okay. Yeah, let me just see if we are connected, right?
Yeah, yes, we are, sir.
Are you connected?
Yes.
Have I muted everyone? What is the deal?
Can you hear us?
Okay. Yeah, good. So everyone can hear me. Okay. Yeah. Yeah. So I'll have to go back to chat. See if you can speak. Just speak. Unmute yourself. Can you unmute yourself?
Yeah, we just unmuted, but I think you can't hear
no,
us.
I didn't try it. Okay, I'll try to unmute you guys. Yeah. Sorry. don't know how to.
Can you hear us?
Sir, are you able to hear us?
Is there a way to unmute? Yeah, I can't hear you guys. Oh, okay. Let me just see. There is some problem maybe. I see. Now, can someone speak? I don't know why I can't.
Yes.
Hear. Yeah, good. Yeah, I think my computer was muted. Sorry about that. Okay. Okay, good. Yeah. So where was it? Yeah. So these are the rings, and this is this matrix is a set of matrices with matrix addition and multiplication is also a ring. But of course, this is not a commutative ring, as we know. Yeah, matrix multiplication is not commutative. You had a course on linear algebra over that. Yeah. This so this you can in fact make it more general. So this entry here. In this R, you can replace it by any ring, yeah? And still you'll get a ring, and which will be a non-commutative ring. So the matrix, when you do matrix multiplication, the entries don't go outside the ring. Okay. So this even if you replace it R by not just any field, but even by any ring, this is fine. So as I said, Q, R, and C are fields. So I suppose you must have seen the definition of field, but let me just recall. A commutative ring is said to be a field if every non-zero element is invertible, has a multiplicative inverse. So in other words, if you remove 0 from the ring R and consider it with this binary operator dot, then then dot restricted to this is a binary operator, and this is a group. So that's a shorthand of saying that every non-zero element has a multiplicative inverse. So maybe one should add commutative ring with a commutative ring R, commutative ring with unity. Yeah. Said to be a field. I mean, if you impose this condition, then unity has to be there. So I mean, this is sort of maybe redundant. Yeah, it follows from this fact. So these are first class of rings. Then another class of rings. So I'm going by what you may have seen earlier. So these things, this number one you must have seen in high school, in school. Yeah, before coming to ISI. This also maybe most of you must have seen, in at least in high school you may have seen this Z mod and Z plus dot. Maybe the notation was different. So of course Z mod and Z with plus is a group, is something which you must have seen in your group theory class, and multiplication you may not have done, but if you multiply two numbers mod and compute it mod n, so there is a that lands in Z mod n Z. So dot is indeed a binary operator, and this makes it into a ring. So one can just verify all the axioms of ring theory. And this third example, which I should have discussed, maybe this should be the 0th example. So if you consider the set 0 with plus and dot, the binary, there is only one way to make the give a binary, two binary operators on them, and they are actually the same binary operator. 0 plus 0 is 0, yeah, and 0.0 is 0. So this is called the 0 ring. So technically 0 ring is a ring with unity, because 0 acts as both the 0 of the ring and also multiplicative identity of the ring. But usually when people say we let R be a commutative ring with unity, many times they may also mean that 1 is different from 0, but sometimes they may not mean it. So anyway, this is sort of a degenerate, some degenerate case, so a special case which one should deal with many times separately. Yeah. Okay. Good. So these notes I'll put it up on the web as well. So as I said, I'll try to give you the board experience. I'll just try to make this small. Yeah. By the way, is this, so those who are following it on smartphone, is this visible? The left-hand side is somewhat visible. Can someone using the smartphone speak up?
Yes, sir. Yes, sir.
Yes, even the left is visible, right?
Yes, sir.
Okay, great. And then right is bigger, so I suppose it's not a problem. So I'll take, I'll make PDFs of this thing and send it to you as notes, so you don't have to copy. And yeah, so if you have some questions in the middle, just unmute yourself and let me know. Okay. Okay, a function map phi from, so now I'm going to define ring homomorphism. So yeah, so a function or a map phi from R1 to R2 is said to be a ring homomorphism if phi behaves well with respect to the two binary operators. So I mean, this is how any homomorphism is sort of defined between two algebraic structures. So it should behave well with all the operations. Like in group theory, there is only one binary operator. In fields, you have two binary operators, special case of ring. In vector spaces, again, there are many operations. First of all, there is a operator on the, so you think of vector space as a group under multiplication, and then there is a scalar multiplication. A scalar, the action of the field on the vector space. So a ring homomorphism should, a vector space homomorphism should preserve all this operator. So same thing for rings or anything you'll see in future. So the homomorphism should preserve all these binary operators. Yeah, so which pretty much means that phi of A plus B equals phi A plus phi B, and phi of A times B is equal to phi A times phi B. Yeah, so that is that's a ring homomorphism. So so maybe some example. So this example one, if you take the map, the inclusion map from Z to Q, it's a ring homomorphism, right? I mean, small as the identity map. So these two relations are tautological. Yeah. So this is a ring homomorphism. Let's consider this this weird map W from n from Z to Q, which sends n to minus n. Yeah. Will this be a ring homomorphism?
No.
No. So what fields?
Phi of A times B won't be phi of A times phi of B.
Yeah, yes. If both A and B are negative, right? So it is a group homomorphism, but it is not a ring homomorphism. Huh? So maybe I'll just put it no. Okay. And then this is the third map. How about this one? W1 from Z to Q. Is this which sends n to 2n? I mean, you can take Z to Z as well. Is this a ring homomorphism?
No.
So which one fails?
The multiplication.
4 times it will become.
Yeah, so it will, so if you, yeah, so phi of n times m is 2nm, yeah, which is, which is not equal to phi of n times phi of m, yeah, which is, this will be 4 times nm. Yeah, and there is another problem with this is so 1 somehow goes to 2. So usually that's not so for rings which are not with does not contain unity, that restriction is not there. But if two rings are rings with unity, then we also insist that this ring homomorphism. So this is not the right example, but I'll give you one example where I mean it will be a ring homomorphism in that definition, but it won't be in this definition. So if you consider R1, R2 to be two rings with unity, then a ring homomorphism phi from R1 to R2 is additionally required to send the unity of R1 to unity of R2. Yeah. So phi of R1 equal phi of 1 R1 is equal to phi of 1 R2. Okay. Any questions? Okay, so let me just tell you one example. Okay, so you consider, for instance, z square, which is you know what z square is, yeah? AB. So this is you do component-wise addition and multiplication. Yeah. So A1 B1 plus A2 B2 is A1 plus A2, comma B1 plus B2, and similarly multiplication A1 B1 dot. So yeah. Okay, I can. Yeah, there is something written there. Yeah, so maybe I should have left some space here. So A1 comma B1 dot A2 comma B2 should be equal to A1 B1 dot sorry, A1 B1 comma A2 B2. Yeah. Yeah, so this is so Z2 will be a ring, and then I can give you a ring homomorphism, and this is a ring with unity. So 1 comma 1 is indeed a is the multiplicative identity. But if you try to send give a map from okay. If we try to give a map from Z2 sending n to n comma 0, then this we can check is a ring homomorphism in this sense, in this sense, but it is not a ring homomorphism in the sense that 1 doesn't go to 1, it goes to 1 comma 0. Yeah, so it's not a ring in this sense. Okay, so let's take a 10 minutes break and then we'll proceed further. Okay, so I'll leave the meeting on because somehow Zoom decided that it's going to not end my meeting in 40 minutes. But I'll pause the recording, and in 10 minutes we'll begin exactly at 11:40. Okay. Okay. Yeah. So let me just briefly go over the previous part. Yeah, since it wasn't recorded, part of it. So this homomorphism sends 0 of R1 to 0 of R2 because phi is a group homomorphism, and another good property is that the negative of an element, additive inverse of an element, is same as multiplying by -1. Yeah, and these are some small these are small proofs, like one-line proof, and yeah. So yeah, there is one more thing which I forgot, is that so there are examples. So this example I did before the break, I think. Yeah, so this is okay. Yeah. Now the determinant map is not a ring homomorphism because okay, so maybe I can add this, since determinant of A plus B is not equal to determinant, is not in general equal to determinant of A plus determinant of B. So I mean, I can write it this way, but when you have to show determinant is not a ring homomorphism, you should give an explicit example. Yeah. So write an example of a matrix A and matrix B, which so this in general. Yeah. So in general. So of course, for instance, if n is 1, then it is a ring homomorph. Then is it a ring homomorphism? Yeah, then it is a ring homomorphism. Then it's the identity map. Yeah. So n equals 1 is a ring homomorphism. Otherwise, it's not. Then we were talking about units in a ring. So so an element u of R is said to be a unit if there exists u prime in R such that u times u prime is 1. And units in Z is 1 and minus 1, and units in Z mod n Z cross are classes of those numbers which are co-prime to 1. And this set has cardinality same as Z, what is called the Euler number. So the number of positive integers less than n such which are co-prime to n. Now that is the size of this. Okay. So so let me give you some different kind of example of a ring and also ring homomorphism. So if you consider a set of all continuous functions from 0, 1 to R, the interval 0, 1 to R, which maybe is in analysis course, it may be denoted by this guy. So maybe I can put a bracket here. So C 0, 1, this is indeed a ring. So you know how to add two functions, and you know how to multiply these two functions. Yeah, so I'll just write it down. F I'll write it in black. This one, F plus G of an element of some x in 0, 1 is just fx plus gx. Yeah, and similarly multiplication. Similarly multiplication. Yeah, so this is a ring, and phi, which maps which sends a continuous function to its value at let's say 1/5. So you can take any number between this. So maybe this is dependent on 1/5. So one can also put a notation here. So this is a ring homomorphism. Yeah. So it's easy to check that this is a ring homomorphism. I mean, this is more or less the definition of these operations on rings. Yeah. So it may look like I've done something fancy. So here you need not consider continuous function. Even if you consider a set of all functions from 0, 1 to R, and you do this operation, still a ring. And this will still be a ring homomorphism. It's just that if you look at continuous functions or functions with more reasonable property, then they are more interesting rings. People study them, yeah. But set of all functions from 0, 1 to R, nobody cares. So that's why people talk about these rings, but not of ring of all functions from 0, 1 to R, yeah. So to demonstrate this example, I don't really need continuity, but these are some interesting rings which people study. Okay, so let me get to this. Am I going at a right pace? Is it too fast or too slow? So if it is too slow, I can speed up, but maybe too slow, you can say a little later. Yeah. If it is too fast, then you should let me know. Okay. So a ring homomorphism is said to be an injective ring homomorphism or a monomorphism if phi is injective. So it's like group. Yeah, group homomorphism. Sometimes it's a injective group homomorphism. Sometimes it's a surjective group homomorphism, and sometimes it's an isomorphism. Yeah, depending upon whether.
Sir, could you please show the previous page once?
Sure. This one. Yeah, continuous functions.
Yes, sir.
Yeah. Yeah. Looks good.
Sir, can you explain?
Identity is there, so you have to check for that one.
Identity. Yeah. So maybe we'll do this example in a little more detail. Yeah. So consider this function f, which is fx equals 1 for all x in 0, 1. Yeah. So this is the multiplicative identity. Yeah. So maybe instead of calling f, I'll call it 1 instead. Yeah. Because I want to have this special name for it. Let me just. So this ring is not just it's a commutative ring with unity, and this is the unit one. This continuous function 1. Yeah. So of course you can check that if I take f dot 1 and multiply it with and evaluate it, it's going to be fx times 1x, which is 1 of x is just 1. Yeah, which is fx. Yeah, so the two functions f dot 1 and f are same. So it is actually a ring with unity. So C01 is, I don't know what's wrong with it today. C01 is a ring with unity. Okay. It's also a commutative ring because the operations f plus g is same as g plus f. Yeah, so it's a really nice ring in some sense. It's not as nice as some of the other rings we'll study. So we won't study these kind of rings that much, but still it's a reasonably nice ring. Okay. So I see there are some chat messages. Let me just see. So. Yeah, so this won't be a ring. If you do composition, that's not, and that may not even be defined. Yeah, so it's not a ring with, composition is not even defined. Okay. Any other questions? Okay. So should we move on from this example? Yeah. Okay. So let me get to this. So a ring homomorphism phi from a ring homomorphism phi is said to be injective if phi is an injective function. Yeah, as a function it is injective. That means it's 1, 1. Phi is said to be epimorphism if it is a surjective homomorphism. If phi is surjective and phi is a homomorphism. And phi is said to be an isomorphism if phi is bijective and it's a homomorphism. So, but usually the definition for isomorphism in the algebraic structures are somewhat different. Yeah, so you say that there should be an inverse, which is also a homomorphism. So it happens that for ring isomorphism, so this is a fact. If phi is an isomorphism, then it's a bijective function from R1 to R2. Yeah. So it has a inverse, which is as a set map, and that inverse happens to be an happens to be a homomorphism in this. So this definition is equivalent to saying that there exists an inverse map, which is also a homomorphism. Being bijective is equivalent to saying that. So maybe one should see this. Yeah. So okay. So maybe I'll put this as an exercise. So check. So this is an exercise. Yeah. So check that phi inverse is indeed a homomorphism. So you will see that, for instance, when you do topology, you'll see that there is a notion called homeomorphism, and so there are functions which are bijective and continuous function, but they need not be homeomorphism. Homeomorphism is like isomorphism in topology, in that category. So when two rings, when there is isomorphism between two rings, that the two rings are isomorphic. So R1 is said to be isomorphic to R2. Okay. So now we'll define some new notions. So we didn't talk about some of these things, but so let me. So we'll go. I've decided to take a route to bring notions as and when we need it. Yeah. So let phi be a ring homomorphism. Then the image of phi is some subset of R2, is a subring of R2. So I haven't defined subring, so we'll define it in a bit. And kernel of phi, which is same as all elements of R1, such that phi of R is 0. Yeah, so it's like in group theory also you have this kernel of a group homomorphism. So same here. So this kernel is going to be a subgroup of R1. It's in fact so like in group theory, you know that this is going to be a subgroup because phi is a group homomorphism as well. If you look at if you think of R1 as a group with with respect to addition. So this is some set which has some structure. It's in fact a additive subgroup of R1. Image phi is an additive subgroup of R2, but it has some additional structure which is called subring, and kernel phi has some additional structure, and that is called an ideal. So subring and ideal will define right now. Yeah. So we'll go. So image phi is defined here, and kernel is defined here. As a set is defined here. Yeah. So let's try to understand what is a subring. So I mean, one can guess what a subring will be. It's like subgroup. Yeah. So let R be a ring and R1 be a subset of R. We see R1 is a subring of R if R1 with these two binary operators. So plus and dot induces a binary operator on R1 and makes it into a ring. So if this triple forms a ring, then we see and that R1 is a subring. So more explicitly, what you want to check is that if A and B are in R1, then A plus B should be in R1. So this operator, so basically this operator restricted to R1 should remain an operator. Yeah, and A and B, if you take A and B in R1, then the product is in R1, and the negative. So if you take A in R1, then its negative should be there. Yeah. So if you insist on all this condition, then this is a subring, and sometimes people insist that one of R1 should also be in R. Yeah, if we are talking about rings with unity. But I mean, in this case, there are many people who don't really care about one of R1 being same as one of R. Okay. So, for example, Z is a subring of Q, and of course, Q is a subring of R, which is a subring of C, and so on. Yeah. So these are all subrings. Of course, there is okay. So I have some space, so maybe I'll put it here. So if you take this definition, all the even integers will form a subring of Z. But of course, I mean so you can check that 2 times Z. So all the even integers do form a ring. Yeah. So, but it's not a ring with unity. Okay, so it doesn't have unity, but so 2Z comma plus is a group, and all the other laws are all the other axioms of rings are satisfied. It's just that this guy is not a ring with unity. But this is so this is a subring. So 2Z contained in Z is a subring. Okay, make sense? Okay. Okay. So maybe go this side. Okay, and then the ideal. Yeah. So let R be a commutative ring.
So,
Yes.
if both subring and the ring has unity, so can they be different?
Yeah, so that's what I said. So sometimes, yeah, so it may happen that it's a subring and and both have unity, and they may be different. Yeah, so it's a matter of convention. So some people insist that the subring may not, the two rings may not have the same unity, but we will have this convention that if both the rings have unity, then they must be the same. Okay. So sometimes they don't insist this, so maybe I'll add this. Yeah. So here, for instance, 2Z doesn't even have a unity, so we can't even talk about it. So maybe convention. R1 contained in R subring. Both R1 and R has unity, then want one R1 to be equal to one R. Yeah. I mean, so these conventions are based on what you want to do. Yeah. So people who want to do want to apply ring theory to various areas, they keep this convention. People who just want to do ring theory on its own, they don't insist on this convention. Yeah. So
the zero ring is not a subring of R.
Yeah, so zero ring is not considered a subring of R. That is true. So zero is considered an ideal, but Yeah, so not necessarily a subring. So I mean, as I said, some people have that convention, that they consider, but we will not think of zero ring as a subring of R, okay, of Z, for instance, in particular. So those which have unity, we won't consider. If all our rings don't have unity, then of course these are all, or some of the rings don't have unity, we'll of course throw all this convention out of the window. But if all the rings have unity and are nice rings, we won't. We would insist that the unities are same. Yeah, so I'll explain maybe later on in the course why we want such a convention. Yeah, why this convention is useful.
Sir, I have a question, sir.
Yeah.
So with that,
Say that again.
no, it wasn't the homomorphism, but that n,0 ring,
yeah,
which was formed, is not a subring of of z square with our convention.
Yeah, precisely. So that's the example one should have in mind. Yeah. So you can think of this set n,0. Somehow it became a triangle. n,0 n in z. Yeah. This set is by one convention. If you by this convention, it's not a subring, but by this definition, if you don't want to worry about units in it, so it satisfies these axioms. Yeah. So when we are thinking studying rings with unity solely, then we won't think of this as a subring. Yeah.
Thank you, sir.
Okay, but so here, so as you can see, this is going to be a ring. This is a subring, but it also has a unity. It's basically this subring. So if you think of it as a ring, is isomorphic to Z. Okay. Okay, so we will. I mean, if there is some confusion, we will specify. Yes, be a little more specific about what it is. Okay.
Sir, if both the identities are in the subring, then they have to be equal.
Yeah, certainly, they will be equal. Yeah. So what you are saying? Yeah, unfortunately, I don't know names. But what you are saying is that if one of R belongs to R1, this implies that one of R1. So even if we were in the previous setup, that means even if one of R1 was possibly different, it can't be different. Yeah? And one of R1 has to be one of R. Okay.
Yes, sir.
Yeah, that is what you are saying, right?
Yes, sir.
Yeah, this is precisely true. So if both rings have unity and somehow one of R belongs to R1, then we would insist that one of, then it will follow that one of R1 is equal to 1R. Okay. We don't even have to insist, but yeah, so yeah. So I'm now thinking whether to, yeah. So let's keep this convention. Yeah. So when we talk about siblings, we'll insist that if both have units, then we will insist unity. Then we'll insist that the unities match. Yeah. So if this follows immediately if the unity of the bigger ring lies in the smaller ring, but otherwise, yeah. So. It's okay. Yeah. So usually these are the subring, and so in many applications, this is what a subring is. Yeah.
So I have a question.
Yeah.
Basically, by taking this convention, are we excluding those subrings which have different unity than the rings itself?
Yeah. This is what technically we are doing. So maybe, okay, so since this is the first course in ring and modules, let's drop this convention, yeah? Maybe this is a good idea. Let's just drop this convention. Okay. So, so later on when we apply this ring theory to number theory, algebraic geometry, etc., when you do more commutative ring theory, so next course in ring theory, maybe this convention will be used. But in this one, let's just drop it. Yeah. But I didn't want to erase this example. So this is a crucial example. So let me just put this in here. So Z is in Z cross Z, or Z square, let's say. In Z square, the set is a subring. Let's give this a name, maybe R1. Then note that 1 R1 is not equal to 1, 1, which is 1 of Z square. Yeah. But if 1 R belongs to R1, then 1 R1 equals.
Excuse me, sir.
Yeah.
So your ink to shape is on. You have to switch it off. That's why the shape is changing again and again.
Where is that button?
On the top right, right, sir.
Now it's okay, right?
Yes, sir.
Thank you very much. Okay. So we'll not impose that convention. Okay, we'll let subrings to have different units. Okay, for now. In later on, if we need to, we will. If there are too many abnormalities happening, we'll insist on that. Okay, now let's come to this this ideal. Yeah, so sorry, I wanted to keep half of this. Yeah, so let R be a commutative ring. A subset I of R is said to be an ideal of R if for all AB in I, A plus B should belong to I. So it should be a group under addition. And then secondly, if you multiply so not only two elements of I should multiply and give you an element in I, but even if you do a scalar multiplication. So even if you multiply an element of R with an element of I, you get a element of I. Yeah. So I mean, this notion you can define it for non-commutative rings as well, but then one has a notion of, so first axiom is same, and if you put the second axiom, it will be called left ideal. And if you put something called, so maybe I'll put this in brackets so that you understand. So there's 2 prime. So this is for, so if it is not commutative, then this will be a left ideal. Okay, and otherwise I, and for all R in R, you want A times R is in I. Then this is called, this notion, if it satisfies only 2 prime, not 2, then you say it's an R right ideal. Depends upon which side you are multiplying the elements of the ring, yeah, left or right. And if in a non-commutative ring, if a subset satisfies all 1, 2, and 2 prime, then you say it's a two-sided ideal. So so good thing about so this so two-sided ideals. So in commutative ring, left ideal, right ideal, and two-sided ideal, they all coincide, obviously. Yeah, and we'll study mostly commutative rings. So but in the ring of matrices, which is non-commutative, one has to insist on this kind of. So this kernel, which we have defined here, kernel is the set of all elements of R1 such that it maps it to 0. So kernel of a ring, the homomorphism, is an ideal. Yeah. So in fact, if this ring homomorphism is a ring homomorphism between possibly non-commutative rings, then kernel is not just is actually a two-sided ideal. So it's not just left ideal or right ideal; it satisfies both the axioms. Okay, and the proof is straightforward. It's one line. So let phi be a ring homomorphism. Then if you have AB is in kernel phi, then A plus B is also in kernel phi, right? Because phi of A plus B is going to be 0. And if R is some element of the ring and A is in kernel phi, then phi of RA is same as phi of R times phi of A. And so phi of A is 0. So you multiply anything with 0, you get 0. So R times A is in kernel phi. Yeah. Similarly, if you do the multiplication on the right, it will give you the same thing. So that shows that even for non-commutative, this is okay. Yeah, makes sense, everyone? Okay, so this is okay. This was about ideals. Yeah, so maybe this was about subrings, subrings and ideals, and so we know that the image is a subring, but yeah, so and so if you note that if we take if R1 and R2 are rings with unity, yeah, and phi is a ring homomorphism in the strong sense that it sends one of R1 to one of R2, then image phi will be a subring of R2 in the strong sense that one of R1 will be same as one of R2. Yeah. So whatever I was trying to take that convention, it won't hamper it. I mean, it would be consistent. Yeah. So let's talk. So we'll talk a lot about subrings and ideals, though it seems like it has come out of this ring homomorphism. They are of independent interest, so we have to study them quite a bit, particularly ideals. Yeah. So let's try to see some examples of ideals. So ideals of Q. So 0, if you consider the 0, the set 0. Yeah. So this is an ideal of Q. In fact, if you have any ring, then the set 0 is going to be an ideal of that ring. Yeah. So this is called the 0 ideal. Yeah. So this is 0 ideal. So this is always an ideal. So there are two ideals. One is the 0 ideal, and Q. If you take the whole ring Q, then also you can check that these two axioms are satisfied, and it's again an ideal. Yeah. So this whole ring is also an ideal. R is always an ideal of R, of any ring R. Yeah. So there are two ideals. Every ring always have two ideals, unless it's the 0 ring, then the two ideals happens to be the same. But if it's a non-zero ring, it will have two distinct ideals. But the good thing about Q is there are no other ideals. Yeah. So why is that? So these are all the ideals of Q. So this, okay, okay, I don't have it written down. So this is, so these are all the ideals of Q. And the reason is, so you take any, so let I, maybe I'll put black here. So this is sort of like notes. So let I contained in Q be a non-zero ideal. So if I want to say that these are the only ideals of Q, then I have to show that I is equal to Q. Yeah, if I'm starting with a non-zero ideal. So what does that mean? So this means there exists A not equal to 0 such that A belongs to I. So A is a rational number A in Q. Yeah, and then of course I want to show that I already contained in Q. I want to show I is equal to Q. So so maybe this is the proof of the above statement. Yeah. So let B be some rational number. Then note that A is non-zero. Yeah. So B over A belongs to the rational number. Yeah. And 8 and B over A times A is equal to B. Yeah. So B over A is a rational number. A belongs to ideal. So this product has to belong to I. Yeah. By the second axiom of this ideal. Yeah. So sorry, I didn't get there. By this condition. Yeah. So that tells you that that B belongs to I. So what we are shown is that every rational number is in I. So this implies I equals Q. Okay. So in fact, what we have shown is there is nothing special about Q. You guys are comfortable with fields, or so this is true for any field, yeah. So anyway, we are not doing too very complicated things about fields. So that F plus dot B field, then the only ideals of F are 0 and F. Okay. You guys are still with me?
Yes.
Yes. Okay. Good. So and the proof is same. Yeah. So of course, 0 and F are ideals, and if you start with some non-zero ideal, then that means there is a non-zero element of F. And in fields, so the definition of field is that every non-zero ideal should have a multiplicative inverse. Yeah. So maybe I'll, since this is the first course, maybe I'll indicate. So it's just the same non-zero ideal, same proof. So let A not equal to 0 belongs to I. Then A inverse belongs to F because F is a field. So in particular, if let P belongs to F, then B times A inverse belongs to F, which implies B times A inverse times A belongs to I, because this is in F and this is in I. Yeah, but this is same as B. So we showed that any arbitrary element of F is also in I. Yeah, so the same proof works. Okay, so maybe it's a good place to stop. Yeah, so or maybe we'll do one more example. So there are 3 minutes. That's enough to do one more example of analyzing ideals. Yeah. So Z is so actually I mean in mathematics you see we think when you're trying to explain it to a kid, integer seems to be the easiest thing to explain, and then you go on to rationals, then reals, and then complex numbers. But in abstract algebra, this is the most complicated ring out of these 4. Then comes the rational, then comes the real, and complex numbers are the easiest to understand in algebra. Yeah. So I mean, hopefully by the end of this course, or at least by the end of next semester, you will be convinced of this fact. So, for instance, I mean, just in the sense of ideal theory, you can see that Q has only two ideals, and so would R and C. But in Z, what are the ideals? So, of course, 0 is there, and Z is there. And what else? So,
any multiple nz.
Yeah, exactly.
Any multiple.
Yeah, so you take any integer n and you consider its multiple. Yeah. So these are this is also an ideal. Yeah. So you can check that this is an ideal, but then so a slightly more non-trivial fact is that these are all the ideals. Yeah. So it's not too difficult, but we will see. Yeah, that that these are all the ideals of C. But still,
These are all the subgroups.
say that again.
These are all the subgroups possible, and ideals are subgroups.
Yeah. So so maybe one way to see is that these are all the subgroups of Z. Yeah. So and ideals have to be subgroups. So that's it. Yeah. So that tells you. But as you can see, there are already infinitely many ideals. Yeah. So it's already in terms of algebra, in ring theory, this is already a much more complicated ring than Q, R, and C. And Q is a more complicated field than R, and R is a slightly more complicated field than C. So when you study field theory next semester, you'll see all that. Okay. So maybe we'll stop and I'll put up a feedback kind of thing. So if you have some feedback, you can share your feedback on how to make this slightly better, your experience slightly better. I hope most of it made sense, and I mean it can't be the real deal, but this is as good as I don't know. We can try to make it as good as possible through this. Yeah. Okay.
Excuse me, sir.
Yeah.
Sir, could you please enlighten us about the marks distribution of this course as well as the assignment which has been uploaded?
Yeah, so this assignment 0 is a fake assignment, so don't worry about that too much. So I'll tell you about the marks distribution later, but there will be, so every week I'll assign, so there will be either a quiz or a homework, yeah? And the marks distribution I'll tell you later, okay? So I think there will be about 4 or 5 quizzes, yeah, and so they will carry some weight, and then homework will also carry some weight, and then there is supposed to be a end semester which will carry maybe about 25% of or something is tentative. So everything, all this is somewhat tentative at the moment. That's why I don't want to tell you exactly what the details are. But there will certainly be homework and quizzes, and there is a grader for the course whose details also I'll share. So if you have some questions regarding the grading, then you can ask her. So what I'll do is in the weekend. So we have class on Wednesday, Thursday, and Friday. In the weekend, by Sunday, I'll upload, or hopefully by Saturday, I'll upload the homework. I'll let you know what the homeworks are, and then maybe you can turn it in by Wednesday. Sounds fair? So you can let me know if that seems a little too less time. Yeah. So you upload it. Maybe I'll give you till Friday. Yeah. So by Friday you turn in the homework, and so I'll try to use mostly I'll try to duplicate both places, but somehow Google Classroom, the interface is more intuitive. So I wanted to use Google Classroom there. So good thing about Google Classroom is you can also make comments on notes or videos and stuff. So if you have questions about the notes or the class lecture, you can just say you have a question at this point, and everyone can see and everyone can respond. Yeah. So hopefully it will be like talking on social media and probably slightly more fun. Yeah. So if you have any questions, you can put it on Google Classroom and we can discuss. Though yeah, so this also reminds me. I noticed that there's still about 4 or 5 students who haven't joined Google Classroom. So I'll ask one of you to form a WhatsApp group as well, and among yourself, to make sure that everyone is part of the group, and hopefully we'll get a response on that WhatsApp group. You can actually I'll email you my number. You can include my number as well. You can form one WhatsApp group with my number too, and if there is some loss of connectivity or something, we can communicate over WhatsApp somehow, because the phone doesn't lose internet, but somehow if power goes out, then I may lose internet. Okay.
Excuse me, sir.
Yeah.
Thank you.
Sir, in the definition of ideal, do we need it to be an additive subgroup, or only the addition should be there?
Once you insist that the addition is there, it automatically. Once you insist that the addition is there, then it automatically ensures that it's a subgroup. Yeah. So remember the definition of subgroup. You only insist that if A, B are in there, then A times B must be there. And
no, in the
inverse. Yeah, inverse should be there. Yeah, but here so that's a good point. So the point
inverse should be there too, according to the second point, right?
Yeah, so
because -1 belongs to R, so -A belongs to I.
Yeah, -1 might not be there in the ring itself. It might not be a ring with identity.
Yeah. So here we'll assume that the ring is with unity. Yeah, that I'll be a ring with unity. So we talk about ideals only in rings with unity. So that's a good point. Yeah. So this is a ring with unity. Okay. So we talk about ideals only in rings with unity. The ring may not be commutative, but it should have unity. So then 2 will tell you that it's automatically it's closed under inverses as well, additive inverse. Okay. Any other questions before we disperse?
Excuse me, sir.
Yeah.
So, in which platform will you be uploading your homeworks, like on your website or Moodle?
So I'll upload the homeworks I usually do it on my website. So I'll upload it on my website. I'll put it on Moodle and Google Classroom, all 3 places. Yeah, I'll just put it on all. But it will so if I don't, what I may do is if I just put it on my website, then I'll put a link to the website in the Moodle. So no, but then you won't get an update. Yeah, so I'll
particular book.
Book, yeah. So I am not going to follow any particular book as such, but you can look at so maybe I'll just write it here. Yeah, so the textbooks. So Dummett and Foote is a standard book these days. There's also Artin, and even Lang is not too bad. Yeah. So these are some books one can. So this is M. Artin, Algebra, and this is Serge Lang, Michael Artin, Serge Lang. Yeah, so Artin and Lang are a little older. Dummett and Foote is slightly newer, but you can look at these books for for reference. But I'm just going to teach from whatever, from my notes or whatever. So the new notes need not follow any particular book in some sense. Okay. Any other question?
Sir, one more request. I think someone has already mailed it to you. Some of us intend to audit a course from B3, the representation theory course, and the classes of the Algebra 3 and representation theory courses are somewhat clashing. So will it be possible for you to reschedule at least one of the classes, Wednesday or Friday, to Tuesday? We have a very light schedule on Tuesday.
Yeah, but Tuesday
it's possible for you.
Okay, so maybe one of the classes I'll try to, maybe the Wednesday class from next week I'll try to move it on to Tuesday. Okay, so I'll see. Yeah, so I'll email you guys. So I can't do both the classes because somehow I'm also helping some master student in some project. Yeah, so there are 2 of those meetings, so I have to coordinate with them. Plus, yeah, there is the rest of the schedule is sort of taken, and one can't put it after 4:30. Some students can't attend it after 4:30, so we can't have it in the much later as well. So I'll try to see. So most likely we can move this Wednesday class to Tuesday. Yeah, and then we'll have Tuesday, Thursday, and Friday. That could be the classes.
So that would be really.
Okay, sure. So maybe I can do that. Okay.
So where to submit the assignment, on Moodle or Classrooms or by email?
Yeah. So initially, I would request you to upload it on Google Classroom and Moodle, both places if possible, so that. See, once I mean, I know how to access it from Google Classroom. Once it becomes easier to access from Moodle as well. So the problem is Moodle is hosted on ISI server, so there may be some issues accessing it sometime if the server is down. So it will be useful if you can upload it both on Moodle and Google Classroom. Okay. So once the homework comes, I'll make these comments in the email when so I'll send an email once the first homework is uploaded and give some instructions. Okay. Anything else? Okay, so if you have any questions, you can always email me. Yeah, and if there are some math related questions, I encourage you to put it on Google Classroom. Yeah, I'll put up this notes. You can put it in comments to this notes, or you can start a. Yeah, I don't know if you can start. I haven't tried that since. Yeah, so last class, whenever I put up when I had put up notes, people would comment on those notes, and we had a reasonably good discussion, and I think it helped people understand things better. So I encourage you to do that. Yeah.
So one last question.
Yeah.
Yeah. So in the subring thing, so we talked about if how like the ring has a different identity and the subring has a different one. So is it possible that the subring has an identity but the ring doesn't have one?
Is that possible?
Like the reverse is possible, so.
Yeah, I don't know. Is that possible? Yeah, I don't know. Yeah, I guess it's possible. For instance, you can take Z cross 2Z. Yeah. So Z cross 2Z won't have a identity because I've sort of artificially removed the identity. Yeah. So you consider this. So this will not appear there. Maybe Z cross 2Z. Yeah, the product this set. So this is set of n comma m, such that n belongs to Z and m is even. M is also an integer, but it's an even integer. So you can check that this will form a ring, okay? And it doesn't have a unity, but of course the subring Z cross 0, this is a subring and it has a unity, yeah? So this is some hooked up example. Yeah, but okay, so these are some esoteric examples, but yeah, it's not something to be worried about too much.
Without our convention, this will happen for every ring, right? We just take the zero ring. If we don't force the two identities to be equal, then the zero ring always satisfies.
Yeah, that too. So zero is going to be a subring if we don't put this convention, yeah. So that's why I said this convention is a nice thing. You don't want these stupid things to happen, yeah. So, but anyway, so right now let's not worry about the convention. Zero ring will always have an identity, and but the ring may not. Okay, is that good? Okay, so maybe I'll end the meeting now, and we'll meet tomorrow around the same time. 11. The class will start at 11:05. Maybe we'll go till 11:35, 11:40, and then take a break and then continue. Okay. That's a bunch of time. Okay. Thanks a lot. Bye bye.